freshman year in Project Lead the Way, we learned a lot of basics about designing solutions. And so we learned about the design process, which is something that we've been using all the years after that.
We spent a lot of time modeling, physical models, mathematical models, and also software models. And the things that they're able to do at the end of the first year in modeling just amaze me.
The Project Lead the Way program really taught me a lot of mechanical skills along with electrical and programming, all the disciplines of engineering.
Really, it's about creativity and kind of just having the ability or the willingness to work through ideas and to really get into things and examine what's going on, how does this work, can I make it better, how could I do that, and what are some great ideas that that might help solve different problems of the world.
We've also learned how to work together in groups and brainstorm, which is something that's really important to do, especially in an engineering career in the future.
It's helped me strengthen my thinking process so that I can go on to college and to these mechanical engineering field and be able to, right out of the gate, know how to think and know how to process things and know how to communicate to other people my ideas.
It's just given me a head start in a lot of the disciplines of engineering that are taught, like mechanical, electrical, and programming. So going into the next step, I'll have a lot of background knowledge about those topics.
I think having background knowledge coming into studying engineering, it's like a big advantage.
The lead up from the past 3 years to this year has been the most incredible journey because we've been able to take the curriculum from the past 3 years and use that to become very good at what we're doing this year.
The highlight of the program for me is really this fourth year Capstone course that I'm currently participating in because we get to put all of the skills that we learned in the past 3 years to use in one final project throughout the entire year.
Being in this course is one of the best things academically that could happen to you.
I think that the program has really helped me learn about different types of engineering and lots of different aspects of things that are very applicable to other mathematical and scientific fields.
So you're going to use these tools now that you've acquired to then make more technical sketches. Again, they're not going to be perfect because these are brainstorming sketches, but you're going to use these to move forward.
PLTW has prepared me after Seneca, not only in problem solving, which is a huge thing that we do here, but also in time management.
Being a Project Lead the Way teacher has helped to kind of broaden my world a little bit. It's let me look out into the bigger world and see where science, engineering, technology kind of all come together to solve bigger problems.
Rather than just teaching them how to do something, I find myself thinking about the inherent science and math concepts and trying to draw those out.
I think that my highlight of the Project Lead the Way program is just how much it's taught me in terms of my future career. I've realized that I want to go into an engineering field because of this class.
The things that we got to do in this class were so beyond what we would be able to do in a regular drafting class or really any class you could have taken at Seneca because of the resources that we have.
I think they come out with empowered to be engineers. They understand the fundamentals of what different engineers do and how to use those skills to make things happen.
All right, hello everybody, and welcome and thank you for coming to see what our amazing Seneca seniors have accomplished. This is a special group of young men and women. When entering the PLTW program during their freshman year, they knew they were going to be sort of guinea pigs being the first cohort for this new program. Throughout their 4 years, they have boldly approached every new challenge with enthusiasm and poise. This final capstone class was no different. On the first day of class, I told them that each of them would be in charge of figuring out what they would learn this year, and that each of them would be learning something different from the others. They at first looked a bit pensive, then they smiled and they said, "Cool." And that pretty much describes this class. They're pretty much like that. During the first half of the year, I was really impressed by their persistence because they spent most of their time on computers doing probably the most thorough research that they had ever done. Eventually, they finally got to start working with their hands, and that's when their creativity really began to take root. They had a lot of help and advice from our panel of engineers, and I'm sorry to call you all out, but if I could just ask each of you to stand and be applauded. We have Mr. Scott Boisvert, Mr. Jim Gupta. We'll applaud you each separately. Mr. Jim Gupta, Mr. Bob Lindaberry, Mr. Jeff Warner, and Mr. Ken Zerone. This panel of engineers volunteered their time and energy to review the students' projects at various times throughout the year. They came and met with me for a couple of hours to learn the program that the kids were using to put their portfolios up, and so that they could interact with the students and give them all kinds of helpful advice, how they were doing on their presentations, what kinds of things they should be thinking about throughout their projects. So their help has been absolutely fantastic this year, and we certainly hope that many of you come back next year. So thank you very much for all of your assistance. It has been very helpful for the kids. So with that, I hope that you enjoy the presentations that we have for you tonight, and that you feel the same pride as I do in the students' accomplishments. Before we get started, I'd like to invite Ms. Heather Zanakis up to just say a few words.
Thank you, Mrs. Carroll. Thank you all for coming out tonight. I also would like to thank you, and I would also like to welcome the students. What a monumental night this is, your capstone presentations, your senior year of the inaugural class of Project Lead the Way. I would like to also recognize a few individuals that allowed this program, Project Lead the Way, to be added to our program of studies. So I would like to thank the members of the Lenape Regional High School District Board of Education, our district and school administrators, Dr. Carol Birnbaum, Jeff Spector, our principal here at Seneca High School, Mr. Cornell, who is here with us tonight, Supervisor of Business and Technology, and Mr. David Mayer, our Supervisor of Math and Science. Our Project Lead the Way teachers, Mr. Jason Pittner, Ms. Ashley Vorwerk, Mr. Rich Watson, Ms. Jen Enos, and of course, Mrs. Dusty Carroll. And our sponsors, which made also this possible, a generous grant from Lockheed Martin kicked us off, as well as contributions from BAE Systems. So I just wanted to give you a little background, as this is the first class of Project Lead the Way. So this journey began in 2013. With a sizable grant from Lockheed Martin to support a STEM-related program. And it was in the fall of 2014 that we began investigating what that would look like with the implementation of Project Lead the Way program. And at that time, both Seneca and Lenape High School volunteered to pilot the program for an incoming group of 9th graders. And specifically, as you know, these students were the students, and there were many unknowns that first year, like who will teach the first class, Introduction to Engineering Design, and what room will they use, and how will we fit the room, how will we fit the space to be appropriate to what the students need, and how will we introduce the idea to the middle schools, because we needed the middle schoolers to be excited about it to apply to the program. These were all questions that we had. And how would we be able to tell if the students were having success throughout their experience at Seneca High School? So what is unique about this group of students is that their sophomore year, their junior year, and again, their senior year, we were asking the very same questions. Again, because they were the pioneers of the Project Lead the Way program at Seneca High School. And throughout the past 4 years, it has been made abundantly clear and that the time that was taken to discuss, to analyze, and prepare for these Project Lead the Way students, these Seneca High School students, which would pave the way for all those to follow, has been worth it. And we are all looking forward to what the future has in store for these remarkable students. So like anything that is new in our lives, we wish to evaluate, we must question and search and refine the process and also the product if necessary. And so these students before you tonight have been an integral part of that initial design process, which has lasted for 4 years at Seneca High School, which has led them to this moment, their senior capstone projects. And at this time, I would like to congratulate the seniors and turn the program back over to Ms. Dusty Carroll. Thank you.
So before we get started, I just want to personally thank Ms. Heather Zanakis and Mr. Dave Mayer. They are sort of the drivers of this PLTW program, and they are just fantastic and supportive, and pretty much everything we've wanted, we have been able to get through their help and assistance. So thank you very much. All right, and if our shopping cart group can come on up. So this is the group of Hannah Packard, Ryan Lawless, and Ryan Eno. They have been our mechanical engineering group this year, so I will pass it on to them. Thanks.
Okay, so we have our design. It's based off a shopping cart. So, can you click it? I don't know if it's working.
Okay, clicker's not working.
That's okay. So when we were narrowing down our problems, we found that the solution, or the problem that we saw was most prominent with people in our class, was the shopping cart wheels and how they become unstable after a long time of use. So we decided to come up with a solution that would fix the fact that they go out of use much quicker than they're supposed to. Usually they're supposed to take 4 to 10 years before they go bad, but a lot of shopping cart companies get rid of them within 2 years. So we went to Murphy's, picked up a cart, thanks to them, and we decided to see what we could fix about it. So our objectives, at first we decided to consider cleaning the cart, because a lot of the time the wheel would become rusted or gross because of how much hair or whatever dirt it would pick up at the store. But then we decided that that wouldn't be quite feasible for us in the time span that we have, so we decided to change it to replacing the wheels, which is where we ended up. Shopping carts, they have cheap wheels, which is why they break so easily, so we decided to create a more affordable, if that was even possible, and a more effective way of replacing the wheels. Past solutions that have already been tried, so companies usually just throw out the cart when they go bad. The cart that we got from Murphy's, it wasn't even the wheels that were damaged, it was part of the cart, like the basket of it. So it just shows that companies get rid of carts without even thinking about it, and they waste money, which is a problem that we wanted to fix. So that's the main thing that companies do when their carts go bad. Another solution was this French company called Clean and Shop. This is when we were thinking about cleaning the carts. You would call them up, they would come over to the shopping center. You would wheel the carts one at a time into this machine, and it would have hydraulic hoses that would clean the wheels. And we didn't see as that would be an effective solution for us because we were focused on the wheels and that cleaned the whole cart. And then another solution is Carts and Parts, which is you can mail your cart to them and they can fix it for you, or you can buy wheels and casters from them to fix yourself.
All right, so for the design process, is that too loud? All right, no, cool, thanks. The first step is always to establish what your problem is going to be that you're going to be fixing. You don't just come up with one problem and automatically you know that's what you're going to be doing. We had to come up with a lot of problems on our own at first, and then we ended up forming groups later, and we all came together, and through a decision matrix, we decided what problem we were going to be doing. A big part of that, as Hannah said earlier, was the time it was going to take to solve this problem. So we had some more problems that were like longer term kind of things, but this was definitely a doable goal. And obviously the next step is to come up with the solutions, and the same way we established what our problem was going to be, you have to come up with many solutions. This probably took most of the time of the class, was coming up with what solution we were even going to try to work on. We probably came up with like 15 yeah, it was 16 possible solutions. Some of them were definitely more doable than others. And we ended up narrowing it down to 3 separate solutions through surveys of our classmates, our teachers. And these are the 3 solutions that we ended up narrowing it down to. It was, the first one was a swivel cart design, we were calling it. Basically, we would get rid of the 4 wheels that were on the bottom of the cart and replace it with the office chair sort of design. We noticed in the classroom, actually, that the office chairs seemed to be handling the floors, which were very similar to a supermarket store floor, very well. And we just thought that it might be a good idea to attach it to the bottom of the cart and see how that went. But when we ended up talking to teachers, they said from a physics standpoint that wouldn't make much sense, and it wouldn't be able to handle the parking lots well because they're just plastic wheels. Like, they're fine on the indoor floors, but as soon as you bring it out in the parking lot, that's going to be a problem. And then our second solution was the snap-on wheel. It's pretty simple, and it's the same wheel concept. It's just the same exact thing. Caster, the thing surrounding the wheel, is exactly the same. But there's a small button on the top of a peg, and it would go into the bottom of the cart, and it would just lock into place, and you could replace it very quickly, just pop it in and out whenever you pleased. The only problem with that was people possibly stealing the wheels, someone said to us, but I don't know why they would do that, so we kind of ignored that small problem. And the third option was we had to come up with a design that was a mixture of possible solutions that we had, and it just so happens this design was also incorporating the snap-on wheel. So it was a snap-on wheel with a brush attachment, and when we brought all 3 of these solutions to our teachers, a lot of them went for the simple snap-on wheel instead of the brush because they were afraid that it would impede the movement of the cart in some way. And we had thought about that before, and we agreed with them, so we did end up going with the simple snap-on wheel. So that's our design right there. Skills needed. When we're working with metal, obviously, if you're going to be attaching metal like pegs to the caster of a wheel, your best option is to weld it. But we've never had any experience welding, so that became a problem. We had to come up with some substitution. We didn't know what that was right off the bat because we don't work with metal a whole lot. But we also had to have a understanding of the physics principles behind the wheel and the friction and the stress that that button would be feeling. So we were pretty prepared for that, but the welding was definitely going to be an issue. Oh, and for tools needed, we need a Dremel to change the sizes of the holes on the cart in order to fit our design. We needed a drill press in order to create the hole in the caster, or in the pipe on top of the caster, and a pipe cutter in order to have the pipes be the right length.
I'm gonna use this. Can you go straight to pictures? Yeah. Good. All right, so I'm gonna start the pictures. All right, so before we could do anything, we need to get the old wheel off. And that was a real struggle, right? Because it was rusted, it was corroded, and if shopping a company like Murphy's, if they can't get their wheels off, they're just gonna throw it out, and that's what we're trying to fix. So it took us about a half hour to cut that wheel off. All right, yeah. We couldn't even screw it off. We needed to get a saw and then cut it off. All right, so after we got that off, we started building our new wheel, which is over here. Thank you. All right, and then first thing we had to do, we had to cut the metal bars right here. And when we used the pipe cutter, as Ryan talked about, you can hold it. There you go. All right, and after we did that, we had to use a drill press to drill holes for the button to go into. All right, we had to do it in both. We don't have the other bar because it's attached to our cart right now. After that, we had to widen the hole in the shopping cart. So if you look at, which one is it? Go to the next slide. Yeah, so if you look in the middle one, that is the other bar. It's connected to the shopping cart. So as the wheel slides up, it connects to the cart. And the original hole that was on the cart, it was too small because it was made for a bolt from the wheel. So we had to widen that hole. We used a drill and a dremel to widen that. After we solved that problem, the next biggest issue was connecting everything. So, add that again, thank you. The metal bar, it needs to be connected to the wheel, and that other metal bar needs to be connected to the shopping cart. And we didn't have any welders, any welding experience. None of us know how to weld. No one that we knew how to weld. So we had to think of some kind of substitute. And the substitute we stuck with was something called JB Weld. It's an epoxy. Now, it gets the job done. It's not nearly as strong as welding, but it was able to connect the bar to what we needed to. All right, and then after that, which took a while, took a lot of trial and error, learn how to connect it properly and have a strong seal, we had our final product, which is right here. Our final product and our shopping cart with the connected bar. All right. Yep. Now Hannah's going to tell you about the results of our design.
So as we wanted to happen, to take off the normal shopping cart wheel, it took 2 minutes and 8 seconds to take it off and about 35 seconds to put it back on. And with our wheel, it only took 9 seconds each way. So we feel like we succeeded relatively. We didn't get all of the wheels done, but we're pretty proud of this thing. So.
For acknowledgements, we have to thank Murphy's Marketplace for supplying us with the shopping cart. Luckily, they just said, yeah, go ahead, take it right away. And just rolled it through the woods to Ryan Eno's house. We also have to thank Mr. Pittner, who's sitting in the back over there. He was a huge help. Without him, we probably would not have finished this prototype by the end of the year or at all. He was really a big help. And of course, we want to thank Mrs. Carroll for just being a huge moral support. She's a fantastic lady. And of course, thank you to all the teachers we surveyed and all the students we surveyed as well. That's all.
Okay, and if our food spoilage group can come up.
Hello. So as we embarked on our Capstone project early in the year, obviously we needed a problem to solve. Like Ms. Carroll said, we brainstormed endlessly, literally endlessly. We used a ton of different strategies, but in the end we arrived at the following problem statement. According to citizen and activist report, in America, a family of 4 each year throws out anywhere from $500 to $1,200 worth of food because it's unclear whether the food is safe to eat or not. And basically the problem is people just don't know if the food's good or not. So they sat on the safety side and they just throw it away to make sure. And it's a real problem in America.
So once we knew what our problem we were going to pursue was, we had to brainstorm what our solutions were going to be for that problem. And we came up with a lot of different ideas, but we narrowed it down to 6 ideas that we were going to focus on. So to narrow those down even further, we created a design matrix. And this design matrix allowed us to narrow it down to 3 ideas. And then with those 3 ideas that we had, we created a survey. And we sent this survey out to teachers who would help us. And then with the results of the survey, we narrowed it down to 1 idea.
So, as you know, our final idea was a sensor that alerts the owner of raw chicken when and as the chicken is expiring. From there, we started our design process, and that was a long one. We researched what we would need to make our idea a reality, which really tested us because we had no idea how to use Arduino or any chemical processes. And we found out that chicken releases ethanol as it expires, so we stuck with that idea. To start, we purchased an ethanol gas sensor, an LCD board, an Arduino, a container, and we coded the Arduino to sense when the ethanol exceeds a certain value.
All right, so as a group, over the years, we've accumulated so much knowledge thanks to the PLTW course, but we found that as we started, we needed a much deeper knowledge on a lot of aspects. Our sensor incorporates all kinds of coding, building, chemical, and biological factors. We also had an Arduino, which was very difficult to handle because in the year prior, we'd only dealt with Robot C, and we had to learn a whole different language of code. We also had to look at what products we were going to buy. This is a description of how our sensor works. The ethanol goes into the sensor and attaches, and it's changed into acetic acid, where it's then changed into electrons, where they're pushed from the anode to the cathode, and the voltage from those voltage and current from those electrons are what the sensor actually uses to read and produce the data for us. Where'd you go to?
So back to our original objective, it was to help aid in the fight of the epidemic that is food waste in America. So as we brainstormed, like we talked about, we had the 6 possible solution ideas, which we then narrowed down to 3 and then 1. But in the end, we concluded that like our best road to follow was a mixture of 2 of our original 6 ideas, which was the smart fridge and the Food Fully app. So our idea, we knew that like this was a good thing to pursue, not only because of like the process of narrowing it down, but because we found research that explained that when chicken spoils, ethanol is a big part of its decomposition process. Yes.
So these were our 6 ideas. The first one was a smart fridge, and as you may know, a smart fridge has a touchscreen outside, and we thought we could have each compartment sense when that food is going to be bad and will spoil, and it would alert the consumer that you should throw out that food. That would cost a lot of money, so we kind of had to go a little bit away from that idea. The Food Fully app is when you input every single food that you buy at the supermarket, and it tells you through median data when it will expire, which that is a lot of work. No consumer wants to do that. And the next one is the milk sensor. So the sensor will pick up chemical changes in milk and will alert them through a color change of the sensor, and it will tell you when the milk has gone bad.
So we also thought of a chat room, which is an online outlet for people to share recipes and talk to each other, and that would help them find ways to use up the leftovers that they have in their fridge before they just throw them in the trash. And we thought of a spray, so you would spray the food that you have, you're worried that it's not bad, or you're worried that it's not safe to eat, so you would spray the liquid on it, and then if the food changes colors, that would tell you that it's not safe to eat. And then we thought of a milk jug. It's similar to the sensor that you would put in the milk jug that Sarah talked about earlier, but in this case, the whole milk jug is actually the sensor, so companies would sell their product in this container, and then that's what would be put in the grocery stores.
So next is our design matrix, which we based on 9 different criterion and weight that we thought was the most important. So effectiveness, cost, ergonomics, technology involved, time, durability and maintenance, performance, aesthetically pleasing, and size. And then with these, we narrowed it down to our 3 ideas, which then led to our final idea. That's our design matrix. You probably can't see it, but it's in our binder by our presentation board, so if you want to see it, it's there.
So with these 3 ideas that the design matrix allowed us to get to, we then went and created a survey, which we gave to teachers in our school. And we gave these to people that either specialized in the the factors that we were using in our products, or if it's a parent who food shops for their family, they would have a opinion on our products as well, because it is about like food and food waste. So we just introduced our 3 ideas in the survey, and then we went and asked questions that would help us just get farther into deciding which was our best option. So the survey allowed us to see that our best winner, or like our winner, was a smart fridge. But instead of like creating a whole fridge, which also didn't match our demographic that we were trying to sell to, we decided to focus on a single compartment of a fridge, which was the the chicken compartment. So we would, so the chicken compartment. So we decided to also combine this idea with the Foodfully app. So that instead of like having this compartment that you would see on the screen, like your chicken's not good, it would actually send an alert to your phone, so you wouldn't have to like deal with the screen.
In the end, all we needed was an Arduino LCD board, all sorts of wires, a breadboard, ethanol for testing, an airtight container, integrated circuit, LEDs, and an MQ sensor.
We also would need chicken, but we didn't get that far, so we did not buy chicken. An important part. So our testing, it was a long time coming. So we found a simulator while all of our orders were being shipped, and we worked on the simulator for a while, and then we set up a breadboard exactly how the simulation was, because it was an analog gas sensor. But then we realized that would not work the way we wanted it to. So we went into kind of a more basic circuit, and that's what our prototype is today. It works. And we coded it with help of Robbie and Reagan, and they helped us finalize a working code. We had some problems along the way. The sensor seems to read a lot of ethanol in the air at Seneca. So we had so our threshold had to be changed, and we figured out how to do that. And then once we changed the threshold, it worked perfectly for us. So that was our main issue. That's our original breadboard schematic that we tried to do, but it was difficult and didn't work great. So then our new design is on the right. It's just an Arduino to a sensor, basic. The light lights up when you put it in the ethanol. And that's our final code. And basically, the threshold starts at 900. You put the sensor over a bottle of ethanol. It reads no, it's fine. It reads the amount of ethanol, and then the light lights up.
When we were doing our testing, we needed 10 milligrams of liquid ethanol to evaporate, but we didn't have the ability to find 10 milligrams of the ethanol. So we needed to do the calculations up here to get it in liters, so we were able to use a micropipette to get the correct amount of ethanol.
So unfortunately, due to time constraints, we were only able to create a simple circuit made of the ethanol gas sensor of the Arduino and the LED light. So when the ethanol values go over 900, the sensor would detect it, and then the light would light up. But that's as far as we got for now. But we do have plans to continue this idea in the future. And even though we didn't get as far as we hoped, we feel like what we did get to was pretty cool, and we're happy that we had this opportunity to do that.
So our next step basically would be to test ethanol values in chicken, and we would do a continuous monitor of it with our serial value page, and then we would look at the data and determine when chicken is decomposing and create a whole new code, and then we would make it something that could be sold in stores, and the price would be around $15. It would be relatively cheap. You just put a little small 3D printed disc thing on your it's hard to describe, on your compartment container, and it would read it, and you could have it connect to your phone once we develop an app, and that's where we're heading in the future. And we have some special thanks to our engineering mentors who were mentioned earlier, our Arduino helpers, our survey takers, our coding experts, and everyone else who has helped us, gave us suggestions and encouragement along the way.
Okay, thank you. Can our fidget toy group make its way up, please? So this is the group of Will Schneider, Austin Gupta, Sebastian Friend, and Sheridan Smith.
Hi, I'm Sebastian Friend, and this is the fidget toy. All right, this doesn't work, does it? All right, cool. Just my luck. So, first, the problem statement and our history. So with the problem statement and our history, we found that people, whether you're poor, young, old, rich, doesn't matter what you are, doesn't matter where you're from, people fidget. People need to do things, and I'm sure many of you are fidgeting right now because this is extended. So, because of this fidgeting, because of this need to fidget in most people, we decided that this would be what we would pursue after, of course, trying to pursue other things and those things sort of falling flat. So before we ended up going for this and trying to solve the fidgeting of people, our first idea was backpacks, but we soon abandoned that idea because we sort of lost steam in trying to do it. Not because there isn't enough to do, but because we just weren't interested. And then the second thing we tried to do was to create a writing app, a mixed writing and music app. But that app sort of fell flat because it became complex to code in the time allotted to us, along with the fact that it seemed that a lot of people weren't terribly interested in it. So eventually, we settled on this. Thank you. So the problem justification. Through our survey, we learned that people fidget quite a bit. And a lot of people are actually very willing to buy a fidget toy. In the top top right corner, you could see figure 1.1. And that was just a 1 to 10 scale in which we asked people to judge how much they think they fidget. Most people said they fidget at least, I don't know, a scale of 1 to 10, 5 or more. And that seemed justification enough to us that people do need this. Our second thing was the amount willing to be paid for such a toy, and that's the bottom right corner. In this amount willing to be paid, quite a sizable chunk were willing to pay at least $3, $3 to $2. Some people were even upwards of 10, or we had one person say $13. So it was clear that people were not only needed to fidget, but were willing to pay money to try and stop that fidgeting. And then in the bottom left corner, we just sort of have that data together. So that's a scale of from 1 to 10, how much people fidget, and then vertically, how, on average, what those people are willing to pay if they fidget. All right, so we looked at a bunch of solutions that already existed towards this fidgeting problem and tried to get an idea of what worked and what didn't. So the 6 things we looked at were the Beglari beads, I can never say that right, and that's that one. The fiddlestick, which is sort of like a fidget cube except sort of pen-shaped, pen-sized, the actual fidget cube itself. The ever-infamous fidget spinner, the roller chain toy, and a tiny Zen garden. And we looked at their shortcomings and we looked at their successes and we judged based on that and based on what parts of the market they had already covered how to make our toy. And from here, I'll pass it off to Sheridan Smith.
All right, so originally we weren't sure what we wanted to produce for our toy, and we looked at many different ideas. One of our ideas was the oval toy, and it was just a tiny toy, had little buttons on it, similar to a fidget cube or other shapes. Basically, it was just a fidget cube in an oval, and you could kind of run your finger along it, almost like a soothing stone, which was another idea of ours, which was legitimately just a stone with a divot in it. Then another idea that we had was the gyro ball. If you've ever seen a gyroscope, it's a little disc that spins along a pole and a post in the middle, and it's supposed to stay balanced. So we were trying to combine a gyroscope and a ball to kind of create a fun idea for people to play with. Then our final idea is a gyroscope, which is kind of a more simplified version of the gyro ball. And so we went around and gave surveys to teachers, to students, and other people who were experts in their field, whether it be mechanical engineering, and as I said before, like teachers and students, people who fidget. Just so we can kind of figure out what the most popular ideas were, what teachers liked the best, and thought would be least distracting in the classroom, because we wanted to create something that students could use in the classroom to help them focus better and to better improve that. So our necessary knowledge and skills, we needed to know how to use AutoCAD, and how to blueprint and how to create these actual things. And we learned that we actually need to learn how to use 3D printers also, which is fun. But a lot of these things we already had learned in our previous 3 years in this program, so a lot of it came pretty easily for us. Then our original solution objectives, we wanted it to be durable enough that you could drop it from, I think it was a height of 5 feet. We wanted it to be quiet so that it wouldn't be distracting in classroom. We wanted it to be fun for the user to use. We wanted it to be a minimum of 1 function at least, so not just something that was useless, essentially. And we wanted it to be school appropriate, like I said before, so that it wasn't distracting in the classroom. But we ended up ultimately bagging that idea and moving more towards the market, because when we interviewed students on what they enjoyed, they weren't interested in the soothing stone or, like I said before, like the little fidget cube, but in a different shape. It was boring, it had already been done. So that's why we ended up actually moving towards the gyro ball, because it was the most interesting for everyone and the marketplace was most open there.
All right, so design iterations and redesigns. So on the left-hand side, we have the original ideas. Some of these are the same pictures, by the way, so if you seem a bit confused if stuff looks similar, that's why. So on the top, we have our end caps. Those are just things that we just put on the end of either side of the pole to make sure it doesn't fly off. Those basically stayed the same because they walked well and they fit our pole. Next, we have our ball bearing holder and hinge. This holds our ball bearings into the as well as locks the toy into a closed position. On top of that, it allows our arms to connect to it and hinge across it. The first one had thinner arms, which broke when we had them locked. The second one we made thicker to make sure nothing broke. It worked, and if you come to our table later, you can see it in closed form and not exploding in your faces. The third one is the arms and how they progress. These actually progress the most. So in our original design, we have smaller 3-inch versions for our original for our small 3-inch size. That didn't turn out well because we had no way to put a hinge on it. The second one, we added the C-clip to it. Unfortunately, we didn't make it big enough for the 3D printer to actually completely print the C-clip. It just kind of ended up cutting off the edge. In our final design, we beefed up the end so the C-clip will actually work. Finally, on the bottom, if you go back, we show the progression of how the toy looks from stage 1, 2, to 3, and how each part was slowly integrated in. On the left-hand side, we have the most basic form. This is when we're trying to get all of our ideas. You can see on the left-hand side, that's our 9-inch, which is our prototype. On the right-hand side, that's our 3-inch, which is supposed to be our final design goal. Over here, we have it without ball bearing caps and hinges on, and that just shows how well the ball bearings fit and how it can lock. We show our materials and arms up there. All of our arms are 3D printed, so that's how we got. That's how we're able to put the arms on as well as the hinges. We have the ball in closed form, and as you can see, the locks work well, and it's not currently exploding into a million pieces. And finally, we have this, which is our walking prototype. Currently, it closes. It doesn't spin very well in closed form because of the friction due to the springs, and its arms are made for its 9-inch form, so those are a bit big. Now on to William Schneider for the final.
So one of the things about our final design is we ended up not making the 3-inch toy, so it is only our 9-inch toy, which you can see here. But as we were testing it and trying to figure out what parts actually worked, we did have another set of the locks, and they broke when we tried to put them together. So we learned a little bit about a stress test in some way that we weren't intending to. Our final design isn't perfect, but it's definitely getting there. And that's what I got.
You have to excuse that slide. I have no idea what happened. It was fine before.
But anyway, we have our acknowledgments. We have Miss Carroll, who taught us. We had Mr. Pittner, who helped us with the 3D printing and actually designing it. And what's the third one? Seneca in general, being that they promoted this program to us and they were very supportive with all the different teachers that worked with us, and the fact that we got half of our parts 3D printed. So we could not have done that without Seneca. Thank you.
All right, can we have our turf group up next, please? This is Carly Toole and Grace Heineman.
Whoops. Like this. Yeah. Okay, so our problem was trying to attack turf fields, current turf fields, because we both come from athletic backgrounds, and when trying to decide what problem we wanted to do, we somehow kept coming back to this one because I think we both felt pretty passionate about it. So what our problem statement was that current artificial and synthetic turf fields are inefficient and dangerous because of the possible harm they can cause to athletes that play on them. Athletes of all levels and also medical professionals around the world are concerned with the tolls that come from playing on them for all ages and all skill levels. So our main goals in this project were to remove the black pellets from turf. I don't know if anyone is familiar with turf fields, but current turf fields have an artificial grass blade, and then they're filled with these little pieces of, it's kind of like ground up tires, pellets. They're black little pellets. And when we surveyed, coaches, athletes, normal people that have played or been on turf before, they all said that this was the biggest problem with it because it retains heat. Fields are like 10 degrees hotter on turf than it is outside, so in the summer that can get insane. And they really just said this was the most annoying part of it. These black pellets also cause turf burn, so if you're playing on a turf field and you fall, all of a sudden you have this big rash and burn, and that can stay for weeks. And it can get infected too. And turf also overall can affect the game in terms of speed of play and etc. So for our justification of the problem, which I already talked about a little bit, technically a lot of professional athletes are not fans of playing on turf. There was an instance where the 2015 Women's World Cup for soccer, they wanted it to be played on turf fields, and a lot of the athletes were upset about it because they don't like playing on turf fields. It changes the game. The ball bounces way more than it normally would, and honestly, it has huge physical tolls on the body that last for weeks after playing, just because the underneath you have, like, if you're playing on a natural grass field, you have natural earth underneath you, as opposed to turf. You don't really have that support that you do with grass. Economically, turf is marketed as being more cost effective due to less maintenance that you need with normal grass, like cutting and watering it and just caring for it overall. But a lot of the time, problems arise that aren't expected to happen. It doesn't last as long as it's supposed to, so it can end up being even more costly than it is with grass. Health and safety, there's been a lot of cases. There aren't any specific proven links, but there has been cases of blood cancers like lymphoma coming up in a lot of cases with soccer goalies who are diving on these black pellets. And if you have open wounds and they're getting exposed to this, then that can be a problem. So it's seen as a possible carcinogen. And like you can really get it, I think there are cases of MRSA too from open wounds getting onto the turf fields where there's bacteria all over it. So yeah, and then legal issues, lawsuits can arise, which is never a good thing. So our well-known prior solution attempts is Field Turf is a really popular company
that has the long pile, common turf, that's like the plastic strands, and then this ground up rubber. And then we had another one we had to say was natural grass, because if you're looking at it, that is a solution to fields. It's just with the field turf or artificial turf, you have the benefit of less care, like you don't need to care for it as much, you don't have to trim it or water it. And then with natural grass, you have to trim and water it, but then you still have the natural effect of the game. It doesn't change the play, while the downside of having artificial turf is changes to the game. But so we kind of wanted to combine aspects of the two of them. So here's a little bit about our design.
So in our early stages, we had to come up with a bunch of different options. And our first thought was, let's try to change the blades, because that'd be cool. And so we came up with an idea of keratin-infused turf blades, because it's natural and it wouldn't cause anyone harm. And then as we went further with that, we decided that's not the problem that we're trying to solve. We have to get rid of the black pellets. So that was knocked off. And then we had natural grass and artificial turf hybrid, because that's the best of both worlds. And that's what we decided to go with. So yeah. We conducted surveys, and it showed that everyone thought that the hybrid idea was not only a really good idea, but it's just cool. And it's something new, never seen before, and it could really work and be the best of everything. So that was kind of our first idea. We would have real soil and then grass inside with artificial turf, our artificial blades. And we decided that doesn't do anything, because you still have to cut it. So that was cut out. And then this was our keratin blades idea, and once again, that's not the problem we were trying to solve, so that was cut out. Okay, yeah, this is the one we went with, because we decided on, we were gonna have real dirt with a polymer matrix to hold in the already available artificial turf. And then we'd put foam in too, so that way you get the support that's not always given with normal artificial turf fields now. And we would have rocks in there so we could have drainage. And this says feet. Not right. It's not a 15-foot deep turf field. It is inches.
So a little bit about knowledge and skills we had to acquire in this process. Material science, obviously, because we're trying to figure out what polymer we wanted to use to make this matrix. Also, originally, we were planning on, or an aspect we would still want to attack, but we didn't get to, would be the keratin artificial blades. So that's materials. And then physics, so we kind of are working with this thing called the coefficient of restitution, and that is the ability to absorb shock. So it's, just for a little background on it, the equation for it is relative speed after of an object over relative speed before. So this is between 0 and 1, and ideally you're going to want, if you want a field that's absorbing shock, which we're claiming that current turf fields don't do a great job at absorbing shock, you're going to want this coefficient to be closer to 1 or smaller, because you want the speed after to be less than the speed before. So if we have, so this is basically like if you're bouncing a ball, or even if a person's falling, you don't want them flying back up. You want the field to be able to absorb this shock. So that's what we're trying to decrease, in a sense, this coefficient of restitution then. So prototype and testing.
Yeah. So this is the same diagram as what we went with before, what we were going to do. The components that we decided to use was the polymer matrix, because that was what was needed to hold the dirt together, because we need a way to hold these blades in place. The turf blades obviously what we didn't go with. They were going to be made from keratin, but not enough time. Our foam foundation, which we turned into polyurethane, like rubber mixture, we were going to have that to make the coefficient of restitution lower, so it was better than already made turf fields. And we were going to need soil and dirt.
So for the foam or this rubber that we're putting underneath the surface, we were originally going to go with a cross-linked polyurethane and polyethylene foam, which is similar to what they use in wrestling mats now. So this would be underneath the surface, so you're not, I know a lot of people were thinking that you'd be like walking on a field that feels like a wrestling mat, which is not what we meant. It would be underneath the surface, so you wouldn't be feeling it on the surface. It would just increase the amount of shock it's absorbing. And our school had a Morim rubber, I'm not really exactly sure how to say it, rubber flooring for us to use, which is similar enough. And it's a recycled material and has little to none hazardous decomposition, which obviously if we're putting this under the ground, that's important to have. And we ended up layering about 3 inches of this underneath our surface as a hope that this would simulate natural earth, or like that natural grass fields have. Here are some pictures of it. As you can see, it's very flexible, and that was the thickness of each sheet we had. It's similar to a surface you'd find on a track, a running track, yeah. So as compared to our original intended product, it had a firmness value somewhere in the range of 40 to 50 at 25% deflection. Both of them did. So for what we're trying to get, this shock absorption, they both pretty much do the same job at it. So in other words, although they aren't the same, this property we're trying to improve if they both enhance, so it works out. So this is a little bit about the polymers.
So our biggest obstacle coming through with this is how are we going to get the dirt to stick together? Because in artificial turf fields, they have artificial things that hold the turf blades together, and we didn't want that anymore. So we found Dirt Glue Enterprises, and they have a wide variety of different polymers and different uses for all of these. So they sent us 3. We took one out immediately, and 2 that we were really interested in was Dirt Glue and Arena Clean. Arena Clean is used in equestrian, like horse racing racetracks, and that's to keep the dirt from flying up, and it allows it to still be like flexible and movable, so that way we would know if it can work for horses, it could work for athletes too, because it's still activities. And Dirt Glue is a polymer, it's like the original, and it's engineered to hold particles of dirt together. So that way it creates this kind of a barrier, and it all sticks together and doesn't just fly up everywhere. So these are some pictures of it. The one on your left is just the dirt glue, and the one on the right is these 2 polymers mixed. So yeah, that's them again.
We ended up going with the dirt glue because Arena Clean didn't really give it, it really just got hard and was in a bunch of clumps, so that really wasn't what we were going for. And the dirt glue, if applied correctly, we didn't really have the right tools to apply it as they would on an industrial level, obviously, but it really just develops this even layer of, like, it brings the dirt together. So that would work perfectly if we're using it to hold turf blades in together. So that would be our matrix underneath, and then we would layer dirt on top of that, so you wouldn't be playing on this dirt glue, which kind of has a little give to it too, which works along with this shock absorption that we're really trying to get. And if you fall on, so we really ended up achieving our main goal of I'm talking about this right now anyway, but we really achieved our main goal of trying to get rid of turf burn while increasing shock absorption, because if you were to fall on this surface, you wouldn't get all beat up from having these rubber turf pellets in it. You'd just be falling on natural dirt. So yes. We didn't actually end up getting to the keratin blades part, so right now we can just use it with normal turf. Because when turf burn doesn't come from the actual turf blades, it's coming from the ground up rubber pellets. So this is just some pictures of our prototype. So that's turf mixed with, it looks like grass, honestly, but that's turf mixed with natural dirt rather than the pellets. That's a foot on it. My foot, actually. There's some pictures of it. No, that's my foot again. That just kind of shows the layers of it. No. We have rocks on the bottom, and then, which is about a 2-inch layer. And then on top of that, we have about 3 inches of this foam I talked about. And then on top of that, we have the blades are going to ideally be rooted in with the dirt glue. And then on top of that, soil. So,
Yes. Well, usually, with big turf companies, they have like really high-tech machines that they can use to test their materials. And we didn't have any of those, obviously, so we just decided to use good old meter stick and drop the balls and see how they ended up. And we did this on artificial turf, natural grass, and our hybrid. And for both things, for both the natural grass and our hybrid, the ball bounced much less significantly than on the turf, meaning they both have greater coefficient of restitutions. So that's good. And, okay. And then, yeah, the baseball was the same as natural grass, how much it bounced up. And the tennis ball, it wasn't exactly the same, but it still absorbed a lot of the shock. So we got our results that we were looking for.
yeah, so as she said, when we tested it on our field and grass as opposed to the turf field we tested it on, the velocity is less coming back up, so that is what we're trying to achieve. All right, so just some acknowledgements. We wanted to thank Dirt Glue Enterprises because they shipped us Dirt Glue Dry, which was the polymer we didn't use, Dirt Glue, and Arena Clean. American Athletic Track and Turf gave us a nice sample of turf, which helped with our prototype. And Merit Service Solutions provided us with rocks and dirts, which were crucial to our prototype. And we also want to thank Mrs. Carroll because she helped us a lot through this whole process when we were trying to figure out what we wanted to do. She really encouraged us to go with something we were passionate about. And I think this whole process would have been different for us if we hadn't been doing something we were really passionate about. So, yeah, that's all.
This is Olivia Spector, Ethan Pfeiffer, and Anthony Johnson. Who's first?
Put it on. Okay.
And then it's the top.
Oh, sorry. Oh, I don't know. I'm
Just
sorry.
close that.
Sorry.
It's okay. It's okay.
I saw synthetic.
That one. And then put it in presentation mode.
Why is it not going? Okay, so like she said, our presentation is the synthetic scab. And our problem statement was that all like adhesive bandages have like a lot of problems, like just going through day-to-day, just wear and tear. And one of the first problems is that people can get infections due to the bandage not being tight enough to the skin and like water getting in or like outside things getting in, foreign things that aren't supposed to be there. Another is that the bandage adhesive can be too strong, which can cause irritation and like redness to the user's skin, and that the bandages don't submerge when they get wet or water, like when someone's like playing sports and athletes and things like that.
Yeah, so after we created a problem statement, one of the first things we needed to do was justify and verify that we really did actually have a problem. So what we did was we created surveys and sent it out to peers and adults such as the nurses and coaches and people that we knew. And we asked them basically just what they thought of bandages currently that are out on the market, whether they believe that they worked well in normal conditions and then under wet and active conditions for athletes or people that work outside and do stuff all day long. And really what the consensus came out to be was that under normal conditions they were all right, they got the job done. But once it came down to when there was sweat or water present or any type of like extracurricular motion and joints and different parts of the body that really aren't easy to keep stable, they really were not that good, and they would come off and fall apart, and they'd have to be going through bandages like all day long just to keep their wound covered.
Okay. These are some of the most like current solutions. These were all found on Amazon.com, and I was looking for like the most commonly bought bandages like that people were buying like today, and one thing that they all have in common is that they're all ranked like 3 out of 5 stars, which was like pretty shocking to me because a lot of people were complaining about like irritation on the skin or like how it wasn't sticking or like, something like along those lines. And we were trying to, that's what really sparked up our idea to like make the gel that we were gonna make.
Press the space bar. Okay, so these were our 3 initial solutions. Our first solution was a hardening gel that would go into a minor wound or like a cut, and it would solidify like over the skin to protect it from the outside. So whether it's like for athletes, like if you get like tackled and you like slide on the ground, or if it's just like washing your hands while you're in the kitchen or after you go to the bathroom to kind of make sure that it's protected, it won't get infected, and that it can just help eliminate some of the problems. Our second solution was a spray-on bandage. This already exists, but we wanted to kind of change it because we talked to some of our peers and like other adults that have used it, and they say it comes off very easily and it's kind of difficult to apply and even can sting. So we thought we would just create like and modify what was already out there and make it more durable for day-to-day uses and more advanced uses like for athletics and like cooking and other things. Our third solution is more out there. It's like a saran wrap type bandage. So you would wrap it around your wound and there wouldn't actually be an adhesive that would touch your skin. The adhesive would only touch itself, so that would eliminate any of the irritation. We thought with this one it would be possible that it would eliminate the problem of like wear and tear, but we found that this might not be as possible.
All right, so we're going to start getting into our design that we used tonight. So our original objectives would start off with just create a new bandage that would be water resistant and that can hold up more than just normal day-to-day wear and tear. We wanted it to, as being all athletes, we wanted it to be able to use on fields and in gyms where it would be quick application, put it on, and athlete can get right back out on the field and keep competing. They don't have to worry about stopping the game because there's blood or something like that. We wanted it to be quick and easy and get the game rolling, so especially outdoors in the fall with fall sports, if there's lighting issues, like if there's no lights outside, want to be able to keep the game rolling, get everything going. We also wanted to be able to hold up against all conditions because there are sports and activities done in the rain or in the snow or things like that where normal bandages just can't keep up. But we also wanted it to be a one-time application. You put it on and you forget about it. Once it's in, it does its job, and by the end, it dissolves slowly and leaves the skin back the way it was. Yeah.
Okay, so the beginning of the design process, for justification and verification, we had to formulate our problem statement. We had to research the problems that bandages were having like commonly. So like yet again, going back to the Amazon slide, we're looking constantly at the reviews of people and like what kind of problems they were having and stuff like that. And we also surveyed our peers, nurses, coaches, adults, everything. And for generating concepts, we have our hardening gel, the spray-on bandage, and the saran wrap bandage. And after like process of elimination, we seen that the most probable solution would be the hardening gel. And we wanted it to be able to harden inside the wound versus on top of the wound. Because if we were to inside the wound, we wanted to like put like medication inside of it to like it like bring back, like bond the skin back together, and we call it the synthetic scab.
All right, so this is the second half of the design process, and after you come up with the solutions, you have to construct a prototype. So once we picked that we wanted to go with the synthetic scab, we figured out, okay, so what's the goal? We want to create a gel first. So we looked into agar, and we liked how agar like solidified and kind of how that would be where we would want the gel to be at once it was in your skin. But through a lot of trials, we figured out that there was no way to create this in a gel that would stay in a gel form, like coming out of a tube, or the application would just be too difficult. So we decided after a lot of testing that we should move on. And then we found a different powder called guar gum, and when it's mixed with borax, it actually creates a slime-like consistency. But we found with this, again, it was too hard and had almost a membrane around it that wouldn't really work to spread or be practical in our solution. We then found two new powders, carbapol and PVP 100, and when mixed with baking soda, the carbapol turns into a gel, but with just carbapol, it's too thin, and that we wanted to see like what we could do. So when we added the PVP, it became thicker and the consistency that we wanted. And the future additions that we would go from the carbapol, PVP, and baking soda gel would be to create a hardening agent, add supplements to aid in healing, and antibiotics to help reduce the risk of infection, test it on living organisms to be able to use it in the future, and the packaging.
So we did have to use a couple different engineering principles and science principles. First off was chemistry. One of the biggest things was being able to find a chemical that we can use that's safe in the body and would be able to actually complete what we needed it to do. So one of the biggest things to know was polymerization, which is used by the carbapol and the PVP as well, to really just take water molecules and all the molecules within the solution and make them into one big polymer, connect them all together to make them into a gel. Next thing was researching chemicals, being able to understand how the chemicals are named and what they mean. Next on was biology and just knowing the reactions between chemicals with the human body and skin. We wanted to make sure that everything we put into our bodies and onto our skin wasn't going to damage anything at all, whether it came down to little tiny irritations in the skin or if the way chemicals reacted within the cells in the body, if it actually would change the chemical compound and ruin the product that we had created. We wanted to make sure that everything was going to be safe and go everything how we wanted it to go.
So for design modifications, we tested different variations of carbapol to water to baking soda, and we've done multiple trials, a lot of trials. And the initial test was to thin the gel because we were making gels that were too thick, and it was hard to apply onto the skin, and we didn't want that. That's not what we wanted. So in our final trial, we increased the amount of PVP to 0.8 grams to a gram roughly, and carbapol the same exact amount. And we kept the same amount of baking soda throughout all the trials, which was about 1 gram, and we had 400 milliliters of water.
And just to explain, I forgot what the baking soda is for. So carbapol actually can't turn into a gel unless you have to mix it with water as well. And it cannot actually turn into a gel if it's in an acidic environment. And we were using tap water, which by nature is slightly acidic. So we had to mix it with a basic substance to make it more basic and try to neutralize the water. And then the final, like I said, was the PVP 100 carbapol and baking soda gel. This gel is only the vessel that will be used to deliver the nutrients into the cut, and it will change properties from a gel to a flexible plastic similar to a rubber band while it's inside of your skin. And the product will slowly dissolve into the body as the wound heals and eventually, hopefully, leaving the body without a scar.
So by the end, we were able to go back and look at our objectives one more time to just see if we were able to meet everything that we wanted to. And we were able to find a good gel carrier to bring into the body and be safe and be able to actually fulfill the first part of the objectives that we wanted it to do. but we really still have a few more steps to go through if we really want it to be a full product. I mean, we want to find a chemical that can make the gel harden and cause it into a flexible texture so that it can be in the body and in the skin without having to cause pain or discomfort. And we also want to be able to add in antibiotic and nutritional properties so that it can induce better healing and reduce scars and any type of unwanted marks. And lastly, we really got to test everything on living organisms, whether it's animals or I don't really know what, but just make sure that it is going to be safe. I mean, you see everything online, but it's definitely better to be able to test it and just know just in case, because anything could happen. And just lastly, just create some sort of packaging that's going to be able to efficiently put the gel into the body or onto the wounds that we need it to be.
We would like to thank all the engineers for giving us a good input on our project. We want to also thank Endeavor for sending us the synthetic skin to test out our gel. And we want to give a special thanks to Mrs. Carroll for all of her help throughout the year, because we wouldn't have been able to get nearly as far as we did without her. And we also want to thank Mrs. Devine for her knowledge with medicine. She was a really big help. She helped us steer in the right direction for this gel, and we appreciate that.
You guys are up. This is Kanan Ladawi and Zach Sinclair.
Some stopped working.
All right, so first I would like to start off with, there's 3 of us, and the kid on the left is Ryan Hartman, and he's currently down in Florida at college orientation. So what inspired our app is Kanan received a receipt from CVS that was nearly 5 foot long, and so our problem statement is, in the United States alone, the American consumers receives 550 billion receipts each year. Of those receipts amount to roughly 250 million gallons of oil, 10 million trees, and 1 billion gallons of water being consumed in their creation. And then also, receipts contain BPA, which is a harmful chemical to the environment, so that makes them unrecyclable. So, that was our original problem statement, and expanding on that, we wanted to create an app that targeted finances, because we noticed that kids our age and slightly older getting into college didn't have an app or a way to properly manage their finances, so we wanted to create an app to do that.
Our concept.
All right, so there are 5 prior solutions. There's 1 grant and then 4 apps. So the grant is what allows us to, this grant is, what was it? It was
The grant is, I can do it. The grant is one of the prior solutions that we had taken a look at, and we wanted to incorporate this specific grant into our final project. This grant is an online receipt keeping server, client-side server, that we wanted to eventually incorporate into our app. The rest of the prior solutions are simply other apps on the marketplace that we took a look at to sort of compare ourselves to in the future and base our design off of. Those apps being?
All right, next we have the Smart Receipts app. It's just basically an expense reporting app. It's all manual, so the receipts that you put in it are all, you have to take a physical picture of it. There's no way that it just sends it straight to the app, which is what we wanted to incorporate in our app. We have the Wally Personal Finance app. It's just basically another finance app, which is kind of similar to ours. Expensify, this creates reports for you, basically like spending reports and savings reports that, you know what I mean, that track your like monthly spending and stuff.
What we found though with it is it wasn't very user friendly. So one of the things we wanted to incorporate in our app was user friendliness, to not put off any customers that might not be so electronically inclined.
All right, next we have the Mint Money Manager app. This app basically just helps you create your budget and manage your bills. All right, so with our final analysis, we noticed that all these apps, while they have a lot of features all combined together, not one app has all the features together. So that's what we wanted to create. All right, so we wanted it to automatically receive and store receipts, generate savings and spending reports, give you a credit score, see and pay your bills, and then manage your budget, and then be free and most importantly, easy to use.
Now on to our design. Some design requirements we had to abide by. Obviously, we had certain constraints that we had to understand. One of the major ones being that we had 6 months to create a workable concept with a base to expand upon. We had to work within the environment that we had chosen for ourselves, the coding environment. We certainly had to have an understanding of the law and understand how to work within the law, especially privacy law and banking law, bank terms and conditions, and the availability of resources to us, such as whether or not companies would reach out to us, like if we wanted to go to ShopRite and ask them to participate, or go to CVS and ask them to participate in our app, whether or not they would do so. So we also had to work with certain parameters, customer needs, performance, target cost, aesthetics, safety and legal issues, ergonomics, operating environment, service life, product life, and durability and maintenance. Just touching on these real quickly, customer needs, the app needs to work. It needs to work with what we want it to do, sending electronic receipts, coupons to the customer almost immediately, having working spendings and saving reports, etc. Performance, the app should be able to do its performance job quickly and efficiently. It has to be able to perform 100% accurately, because when it comes to finances, one little misplaced decimal or comma can mean a lot of problems, either in the future or at the time being. Target cost, we wanted the app to be free. One thing we noticed is that most finance apps were free. After all, you're using something to deal with your finances, you don't want to spend any more money. However, the more in-depth features, such as paying bills or being able to look at stocks and bonds, or even purchase stocks and bonds, which would certainly cost money for us to be able to have access to as programmers, we would have the app cost $3.99 every quarter year. Aesthetics, we didn't really want to put too much effort into aesthetics. Really, it's a finance app. You're not really going for pretty pictures. Something smooth, something easy to look at, something pleasing to the eye, but nothing too crazy. That wasn't the main concept. Safety and legal issues, client security and confidentiality would be one of the most important things to us, because in this day and age, safety, data safety, client security is one of the most important things to people. They want to know that their data is going to be safe, especially when it comes to financial matters. They don't want anybody else besides them or certain loved ones that they may choose to have access to their bills or to the stocks and bonds they may have. So we certainly wanted to, if we got to the chance to actually get this to fruition, we certainly would have taken a very deep delve into safety and legal issues. Ergonomics, like I said before, the app, we want it to be absolutely user-friendly. It's the point where somebody who isn't as tech-savvy would be able to handle it without any issues. With that, though, we would need to incorporate everything we wanted to achieve. In our operating environment wasn't too much of an issue. Really, you can code so long as you have a computer that can, so that wasn't much of an issue for us. Service life, most successful apps we found after doing some research are updated 1 to 4 times every month. Depending on in-app bugs and user reviews, we wanted to have sort of a roadmap for users to tell us bugs that we would be able to fix 1 to 4 times a month. Product life, obviously, we would want to have it updated 1 to 4 times a month, keep it for long possibilities, because finances, they're a long-term thing, saving especially. So we'd want the app to be able to last a long time. Durability, obviously, we'd have to have frequent updates for bugs and glitches, around 1 to 4 times a month. We wanted the users to have access to see what the code would look like for anybody who would have a greater understanding of coding than we may have, to be able to tell us, hey, you do this, and it'll make it so much better. The actual coding of our app. Before we began, we had to decide on a coding language as well as a platform. We decided, based on several factors, learnability, ease of use, efficiency, accessibility, deciding on Kotlin, mainly because it was an up-and-coming coding language. It's very easy to learn. It's very compact. It's supported by Android, and we felt that it would be best for what we were doing. For a platform, we began coding using a platform called Eclipse Oxygen. It had active Kotlin support, and it was easily accessible, being free. However, we wanted to, as we were coding, see how the app would look, and Eclipse didn't have that feature. So we ended up moving over to Android Studio, which is supported by Android, has active Kotlin support, and as we will show you later with our prototype, you can actually see what the app will look like. Coding, we split coding equally amongst the group, and we were going to put the parts together at the end. I worked on the login screen. Ryan, who's not here, worked on button functionality, making everything go together, and Zach worked on the main menu and functionality of that. Our actual product. Here we just have a couple pictures. That is what the login screen looks like. I'll show you on the actual device. The picture on the right, this is our main menu. That is what it would look like on a phone before it stopped working. It was working before we left school today. We came in and it stopped working. So gotta love it. But here I'm going to tab out and move over here. And you might be able to see it, possibly. This is what it looks like within the app. It shows us the parameters, the actual the constraints. That is our main menu, and I believe I can look at, this is just simple text code that we had to work out in order to have everything in the space that we want it. It's a lot. Oh, that's not it. And then this is our main menu. We would want, obviously, to have it based on an account system. So they would log in either with a Google account or with account for our actual app. And this one, I believe, no, it has as much. That's the coding for it. Some acknowledgments. We want to thank Seneca and the Lenape High School District for allowing us to participate in this program for the past 4 years. They've been incredible. We made a lot of friends. We made basically a family. Going to miss everybody going off to college. Wanted to thank Ms. Carroll for having unwavering patience. I know I scream a lot when things don't work, so thank you for having unwavering patience and for taking so much time and putting so much effort into helping us succeed. We want to thank the Seneca Tech Department for essentially waiting on us hand and foot while we were attempting to set this up, the computers and working in the school computers, because I know how to do it. I just didn't want to get in trouble. We wanted to thank the engineers for being a guiding hand and we want to thank everyone involved in helping us throughout this past year.
Okay, can the water bottle group come on up? So this is Sam Durgas and Brady Moore.
Hi everyone, I'm Sam, this is Brady, and we decided to create a biodegradable water bottle that would work for our project. But before we begin, we just wanted to acknowledge all of the engineers that helped us, Miss Carol, our wonderful teacher, and a lot of the people that we surveyed, including some of our teachers and parents and everything.
All right, so our problem statement, we basically realized that plastic emissions are a huge problem in America and across the globe. Plastic water bottles contributing to most of the plastic emissions. We realized that this is not only posing a threat to our environment, marine life and whatnot, but it's also posing a threat to human health. We looked up some statistics based off of water bottle emissions, and it's pretty insane how much water bottles there are in the ocean and across the world that people throw away. The background of our problem, we both had a mutual interest in environmental sustainability, environmental health, and human health. Like Ms. Carroll said before, I'm super into science, Sam's super into business, Sam's also really into art. So that actually really meshed really well throughout the project, and we wanted to base it off of those aspects of our personalities.
All right, so real quick, as our engineers can tell us, we've done a lot of surveys this year, so we wanted to take sort of a group survey. So raise your hand if you've used plastic water bottles, ever, at least. Okay, now keep your hand raised if you recycle your water bottle every single time you've used it. That means whether or not there's recycling there, you don't throw it out, you don't litter it, keep it up. Okay, so a lot of hands went down, and that was sort of our basis off of this, was that we realized, oh my gosh, we might recycle, but recycling isn't available all the time, and every time a water bottle goes into a landfill, it's there for hundreds of years before it actually decomposes. So we wanted to create something that didn't have that same lasting effect. But when we did our research, from that we found what we were trying to accomplish couldn't be achieved because it was too expensive. Some of the ideas already out there are super, super expensive, or they're out there. So when we're trying to sell to a customer, we're not going to have that same basis that a plastic water bottle has of being reliable because they think, ooh, that looks gross because it's natural, or we don't know what it's made of, so we're not going to buy it. And we also had to be able to compete with these other companies who have been so long established that they can sell to big corporations and they can sell to lots of companies, but we have to create something that can equally compete with that. And some of our past solutions, like we said, they're either too expensive or they're just far out. There was a idea, instead of a plastic water bottle, it was actually a bubble that you ate and it was filled with water. Some of them were just so weird that we're we need to think of something that's going to be cheap and it's going to be somewhat normal so people will actually buy it.
All right, so the knowledge and skills. We knew going into this that we were going to need some chemistry skills, and we were going to need some chemical engineering help with this. More chemical engineering than we actually thought from the beginning. We also knew that we were going to need a knowledge of general biology and health. You can't make a water bottle that's poisonous. That would kind of suck. We also needed knowledge of the way materials act in their environment. So this is our prototype, as you can see up there. Sort of an opaque peanut buttery type look to it with a cork at the top.
All right, so to get to this stage in our process where we have a working prototype that will actually hold water, we had to research these past solutions and think of ideas that would, number one, be cheap, but also that we could achieve in this short timeline that we had to actually make something. So we actually started doing a lot of testing, and we wanted to use cellulose right off the top because it was so abundantly found in nature. But we found out it's water soluble, which is not good when you're creating a water bottle, considering it wouldn't hold anything. So then we switched over to chitin, and we created our first prototype by mixing it with wood flour. And then from there, we've been sort of working along a process to create this perfect solution that will work along with our molding technique.
All right, so our original objectives, that's a goofy picture of me up there, you all can enjoy. So our original objectives, obviously it's a water bottle, so it's got to hold water. You know, that's a shocker, I know, but that was one of our objectives. It needs to cost really not a lot of money. The economics of it was a big aspect because, you know, plastic disposable water bottles are super cheap, and that's a reason why they're so popular. So we needed to make it as cheap as possible, just so it could compete with those bottles. Yeah. And we also, it had to be biodegradable because it's a biodegradable bottle. So that's it. One of our big design decisions we had to make was switching over from cellulose to chitin. We started off with cellulose because it's the most abundant protein in nature. So we figured it would be good. You know, it's biodegradable. It seems to hold a good structure. But then when we found out that it was water soluble, not a great plan because, you know, you don't want your water bottle dissolving when it touches water. So we switched over to chitin, which is the second most abundant plant protein in nature. Not water soluble, so that's a plus. And there's already been a lot of research involving chitin in the world, you know, specifically in Harvard University has done a lot of studies with it and how to mold it and molding industrial chitin into products. So our procedure, we used some of Harvard's research to base our procedure off of. Basically, they did research, as you can see up there. There's a picture of some cups that they made using chitin and chitin-based materials. They created this synthetic plastic. Some problems we saw with that was that when they created it, it shrunk a lot. It shrunk to like a third of its size. So molding and scale of those plastic products was a real issue. So with our product, we changed the recipe of Harvard and the procedure, and we also changed some of the ingredients we used to make it shrink less and to make it stronger and less brittle overall.
So to refine this process, I like to call it the secret sauce because it's basically a substance. And we wanted to find a good balance between using the chitin and then the wood flour, which is our component to keep everything together. And the problem was when we used too much wood flour, it was too brittle, and every time we would drop it or move it, it would just break. And if we used too much of the chitin, then it was too loose and it wouldn't really hold the water. So it was sort of like that Goldilocks effect, I guess, where you're trying to figure out exactly how much is enough of each of the substances. So that was a lot of refining it to figure out exactly how much we needed. And then we also had to go to Mr. Dooley for our molding process, which was the artistic component of it, to find out for this molding process how exactly we were going to take this substance and create a water bottle out of it. So we ended up painting it onto current bottles, and it allows us to be able to make our own molds so that when we decide to manufacture it or produce it, we can make it as convenient as we so choose. And then for our next steps, it's really just about refining it and making it so it doesn't smell like any of the ingredients that we use, and it successfully does hold water for extended periods of time. And then from there, we want to distribute it, and that's where a lot of the business aspect comes into it, with selling it and creating a good price that can actually compete with current plastic water bottles. So that was basically what we had going, and we know that our product can be successful because all of our materials are organic, they're very cheap, and our design process is simple enough that we could manufacture a lot of these bottles for a very cheap cost. So really the only step that we have left is to get that customer-client relationship going so that we can actually sell these bottles. And that is our project. Thank you for your time.
Okay. Okay, our next group is going to start with a video because one member of the group had to go to college. She started college last week. So, Mr. Seeley, if you can switch control over to you and start the video. The video is going to be Melanie Weaver, and her group is Shannon Briggs and Morgan Calabria. These girls actually took, I was surprised by this, I have to say, because their sophomore year, they had me for environmental sustainability, and everybody always made fun of how long we spent on the water unit. And these guys decided to do a project on just that. So, with no further ado, Melanie.
So as you guys know, I'm obviously not here right now, so I'm going to tell you why that is. I'm Melanie Weaver, and I am at college right now. I had to leave a few weeks ago, so I couldn't be here for the presentation, but I still want to share with you about our project before my group mates continue. So I'm going to just start out with that. So our project is oil spills. To begin to decide what problem we chose, we did a problem matrix with different types of criteria. The criteria we used are whether or not the problem can be accomplished within the given time, can it be solved with our available resources, does the initial research indicate that the problem truly does exist, is the solution likely to meet a specific need, is the problem interesting enough to keep us interested in it and wanting to continue, is the solution marketable? And do we have any prior experience with the topics that we would need? And do we have any possible expert contacts? And through this, we used our different ideas and weighed them, which our ideas were drinking and driving, speeding while driving, mascara drying out, oil spills, ocean water purification, sunglasses getting stuck in your hair, and glass fogging up. So based upon this, we decided to go with the oil spill problem. So our problem statement is that oil spills have worldwide effects and a solution needs to be developed to prevent these effects from continually reaching extreme levels. Millions of gallons of oil enter the ocean each year from factory wastes and other means of pollution. In a typical year, according to the U.S. Department of Energy, 1.3 million gallons of petroleum are spilled in the U.S. waters. The oil waste then goes on to damage the shorelines, vegetation, aquatic life, and swimming locations. Due to all of this damage and the inability to quickly and efficiently resolve it, oil spills have negative impacts on the economy as well. For example, after the BP Deepwater Horizon oil spill, the company suffered $62 billion in damages. This same spill negatively impacted the fishery and the tourism industries on the Gulf, which produce a total of about $4.5 billion each year.
Okay, I'm Morgan Calabria. This is Shannon Briggs. So first we're going to talk about some of our design concepts that we thought of when coming up with solutions for this. So some of our preliminary solutions were we decided to combine the, this oil magnet that's being produced by MIT and then a biocleaner that kind of looks like a Roomba vacuum but like for water, created by this Chinese guy. And basically, they each have their own flaws, which is why neither of them are really in use right now. So our first idea was to combine them to create a product that's more like covers all the oil. And then our second solution was MIT's magnet uses iron, which can be harmful to the environment, which is why it's not currently in use. So we had the idea to switch out iron for cobalt, which is like a metal that's not as harmful for the environment. And then our last idea was, well, one of our last ideas was to take out some of the complex parts of the biocleaner because there's not really technology around that can create this kind of product. But obviously we didn't have the technology for that either. So our last, after we had all of these ideas, we kind of had to go back to square one and find something different, something new that had never been thought of before. So after a lot of research, we found milkweed, which we had actually used something similar to this in our sophomore year program. And there are little white fibers that are hydrophobic and oleophilic. So basically they repel water and attract oil naturally. They're very cost efficient, and they grow. They're obviously natural, so they're not going to be harmful for the environment. So what our idea was to create like a blanket out of this milkweed, and put it over the oil so that it absorbs the oil from the water. And it can be removed pretty easily, and it's friendly to the environment and all that kind of stuff. So one last thing that we had to think of, because this is like in the ocean and it's a natural thing that we can't just let it sit there. So we had to think of a way to clean it up. This is an idea that we didn't really attack that much this year because we were trying to come up with the idea for the milkweed blanket. But basically, we came up with like a very preliminary idea of making nets that are hydrophobic and oleophobic, that won't absorb any of the oil or the water, and will pick up the milkweed when it's laying on the ocean so that none of the fish eat it.
So I'm going to start taking you through a little bit of our design process. So since basically our entire project was a series of complex chemistry experiments, we had to do a lot of background research before we even started to get our hands dirty with the milkweed. We had to create a lot of design specifications to make sure that we were attacking the right goals throughout the entire year. So some of our specifications for the form of the actual product, we wanted to make sure that the sorbent at the end would remain floating at the top of the water and not sink down once it was placed in the ocean. So we did a little bit of research. We found that the average density of oil is 0.93 grams per cubic centimeter. The average density, or the density of water, is 1 gram per cubic centimeter. And after a little bit of testing, we determined that the density of the milkweed soaked in the oil was only 0.721 grams per cubic centimeter, which means we achieved our goal and it would float. We also knew that we wanted the blanket at the end to be weaved or braided out of just the milkweed floss and nothing else. We didn't want to pollute the environment at all. And we wanted to make sure that the sorbent in the end would fit on a helicopter or a boat or something so that it would be able to get to the middle of the ocean, but obviously we couldn't test that in school because you can't fit a helicopter in Seneca, so there's that. For the function of the sorbent, we wanted to make sure that it would hold multiple liters of oil before we had to take it out. With our testing, we were only able to use up to 250 milliliters of oil per experiment, so we scaled it down a little bit. But with the smaller samples of the milkweed that we used, some of our experiments actually only left behind very little oil in the water. A lot of them actually soaked up all of the oil that we put in there, which was pretty great. We were pleasantly surprised by that. We needed to make sure that the milkweed would withstand being hit by waves if it's going to be in the middle of the ocean. So we did some experiments to test that, and we found that splashing water on it did not negatively affect it whatsoever. Again, we needed to make sure that it was safe for the environment and that it required minimal to no maintenance. The materials that we used, we wanted to make sure that we were just using the milkweed floss, again, just to protect the environment. It's naturally abundant, so it's not causing any harm to the marine environment or anything else. It obviously needs to be waterproof, but milkweed is hydrophobic, so it worked out. And then for the aesthetics, we weren't really too concerned about that because it's essentially just a blanket to clean up oil spills in the middle of the ocean. So who really cares what it looks like as long as it's really getting the job done? We're here to protect the environment, not make something pretty. But we knew we wanted it to be a sort of blanket, so that's as far as we got there.
All right, so for the ergonomics, this doesn't really apply as much to the milkweed as it did to the net that I talked about earlier. So we just kind of like laid down some brief description with like the handle of the net and like the holding of it and how it needs to be comfortable for the person that's using it. And another thing for the milkweed, the only really way this would apply would be when you're dropping the milkweed in to the ocean and how it needs to be able to fit in a boat or a helicopter so that it can actually like do its job. So some legal and safety issues. There is this act called the Jones Act, which provides like seamen with the right to sue employees for like negligible behavior. So we basically had to make sure that our product would be safe for all the workers on like the ocean and all that kind of stuff. So obviously we wanted this to be cost effective. If it was super expensive, then it wouldn't really like do any better than any of the other things that we were looking into, the like really high-tech designs. If this plant can't do any better than that, then that's kind of pathetic. So we had to make it cost-effective and make sure that the price was really low. And for our customer needs, like this was one of the biggest reasons why we did this, because it's so like prevalent, the harm that like oil does on society, and like not just like animals, but it like affects people too, like the tourist industry and all the things that we looked into. It's super harmful, and we like this was something that was really easy to go off of. So we had a lot of different experiments that we did for this. Like after we decided that we were going to do the milkweed, we had to figure out a way that it best soaked up all the oil in different like environments. So we definitely wanted it to be only made out of milkweed, and we had to decide whether we were going to focus on great surface area or great mass in the ocean, and had to simulate all ocean scenarios. So some of the skills we needed to learn how to spindle. Shannon was kind of our like spindling, weaving expert, or she tried to be. We watched a lot of YouTube videos trying to figure out how to turn this milkweed into a blanket. And then actually all three of us took AP Chemistry last year with Mrs. Carroll, so we had a lot of chemistry background, which was awesome. So our first experiment we did was our control experiment. We kind of just like, we got these, if anyone saw them in the cafeteria, we got giant bags from this Monarch Butterfly Ranch, and we just reached into the bag, took a big handful of it, and plopped it down into our experiment. We had 250 milliliters of water and 250 milliliters of oil, which the best way to simulate oil that is used like in the ocean would be 15% of the diluminine and then 45% canola oil. So that's the mixture that we had in our experiment. And so we would drop the milkweed in there. And then afterwards, these were the results of our control. It kind of just shows how much of the oil was sucked up, and like you can see how like most of the oil and all of them were like extracted out of the water. And so then we looked at those results. Wait, I'm gonna go back, sorry. We looked at those results and saw how like the tightness of the little clumps that we put in the water like made a difference of how much oil was soaked up. So then we decided to pursue that, and like our next experiment was we would take the oil or the milkweed and like crunch it up into little balls of like different tightnesses and put that in the same amount of oil and water and see how much each one, like in a 24-hour period, how much oil it soaked up. So in the first one, which here it says that the first one was the tightest, the middle one is, oh sorry, I'm pointing to the wrong screen. The middle one was in the middle, and then the last one was the loosest. So the first one had 75 milliliters of oil left, the second one had 72 milliliters of oil left, and then the last one had only 42 milliliters of oil left. So that shows by just kind of like, it's the same kind of concept where we just kind of put it on top of the oil. It shows that having a lot more surface area is what's more beneficial to soaking up all the oil.
And in doing these experiments, we obviously wanted to make sure that the milkweed would soak up oil in an ocean environment. So just sitting it in some tap water and oil isn't really going to tell you how it would work out in the middle of the ocean. So we went to simulate the crashing of waves over the milkweed. And we used the same mass of milkweed for each experiment. We used the same 250 milliliters water, 250 milliliters of oil to simulate the ocean waves. We put it in a graduated cylinder and we shook it up to move the water around and poured more water on top of it. And this actually left 0 milliliters of oil in the graduated cylinder after we removed the milkweed. And there were 246 milliliters of water left, so it only absorbed a very slight amount, and that was just in like pulling it out. After we tested the waves, we wanted to put it in some salt water, again, to simulate the ocean. In this, there are 35 grams of salt per liter of ocean water, so we scaled that down and used 8.75 grams of salt because we're working with milliliters here. Again, there was no oil left after this experiment, and there was even less water that was absorbed when the salt was added into the equation. And we found that in this experiment, it was actually much quicker than any of the ones we had done before. All of the oil was gone in under a minute time, which was absolutely amazing and just gave us so much hope for what's to come if we actually get this to a full solution. So the objectives, we pretty much met almost everything that we wanted to except for creating the final prototype. We made a product that was solely milkweed and nothing else. We determined that greater surface area was really what impacted the experiments most. We simulated a bunch of different ocean scenarios, and they proved that the milkweed actually works better in those situations than it does when just sat on top of water. And we absorbed all of the oil from those experiments also. So our final product, we didn't actually get to complete it entirely, but this is the process that we went through. So basically we started out all the way on the right here with a big bag of milkweed floss that was sent to us from the Monarch Butterfly Watch, which was very generous of them. It's the floss from inside the seeds of the actual plant. And from there, we took the spindle and I rolled out the floss into these long strings as much as I could, and then wrapped it around the spindle and, sat there and meticulously strung it out for a while. Pretty tedious, but the middle picture shows what that gives you. It was really hard to make them very long and very thin because, as you know, I was doing it by hand. So the problem that I encountered was doing it by hand and not having a machine to do it for me. That's how all of the other blankets and clothing is produced in the world. So we figured that the final product that we want is the blanket pictured on the end. But if we were to use factories to produce this, it would definitely work. Unfortunately, we didn't get that far because we don't have industrial materials at Seneca. But we really believe that if we were to manufacture it industrially, it would certainly get to the point where this would be a viable solution. All of the parts are there, they just need to come together. The milkweed soaks up the oil very efficiently. It absorbs very little water, if any at all. The fibers are definitely able to be spindled into strands, even by hand. So imagine what they could do if they did it in a factory. The fibers occur naturally in the environment, so it's not going to harm anything. And experts agree that this is definitely something that's worth pursuing because you're not only just cleaning up oil from the middle of the ocean, you're helping the tourism industries, you're helping save the environments. And what we found also with the milkweed that we didn't show, because it was one of the last things that we did, was actually when we were to take the milkweed out with the oil absorbed into it, we were able to squeeze out almost all of the oil that was absorbed in the first place. So this shows that we would actually be able to reuse the milkweed sorbent after it was used once, which is different from anything that's out there already. That was the biggest thing. There's so many different substances that make the sorbents now to clean up oil in the ocean, but all of them are like a one and done situation. You use them and there's no way to get the oil back out, so you pretty much have to throw it away. So the next step that we were thinking of was how to retrieve the oil-soaked milkweed from the ocean, and we designed this net on AutoCAD Inventor, but we didn't have enough time to actually physically build one. But the netting would be made out of polyethylene because it's both hydrophobic and oleophobic, so it wouldn't absorb any of the liquids that were involved. It would just pick out the sorbent, and then you would be able to squeeze out all of the oil, or almost all of the oil, potentially reuse the oil in some other fashion, and then also be able to reuse the sorbent itself. So for some acknowledgements, we want to thank everybody in the LRHSD administration that helped the PLTW program come to Seneca. It's been an awesome 4 years, and this capstone course has been absolutely amazing, being able to work on this project and really come up with something that seems like it could really go somewhere in the future. We want to thank all the engineers that guided us in this process and reviewed our innovation portals and helped us when we really didn't know what we were doing at the beginning. We want to thank Monarch Watch again for sending us all of that free milkweed, which was great, that we barely used any of. And obviously Mrs. Carroll for always being there for us no matter what we needed at any time throughout the entire year. Just really helped. That's all.
Thank you. All right, so I'd just like to lead a round of applause for all of our presenters tonight. Okay, everybody did a great job. I hope you all enjoyed their presentation. And now if I can have Mr. Dave Mayer come on up and say a few words.
That's all right. I'll use this one. Okay, I'm going to also just want to say a couple things. First of all, let's give the kids another round of applause. What an awesome job they did, and I'm very thankful for their hard work and their perseverance in this program. They had to sacrifice a lot to go through a program of 4 years, which essentially ate up one of their slots in their schedule, and I'm very grateful for them. I want to thank their parents for your dedication to your students. They reached a milestone in their life right now, and you were part of that journey. As they approach graduation, as they approach the end of this program, we are very grateful here at Seneca for your willingness to help them. I'm sure you helped them behind the scenes as they progress through this project, and I know you helped them throughout their 4 years here at Seneca, so thank you for that. So I remember when we as the Seneca administration volunteered to run this program, and we sat down with all this information about these students that wanted to come to Seneca and join this program. And it was a lot of numbers and data and just names on a page. And 4 years later, here we are with the first graduating class from our engineering program. And you know, in my eyes, have become so much more. And these presentations that they made just verify that. They have set the bar for what this engineering program will produce. And I know that, I know we have some people from, students that are entering Seneca next year, and hopefully some of our students that are currently here. And I know that you guys have really set the bar for those students and given them an idea as to what these projects entail. And I want to just thank you. I know Mrs. Carroll appreciates that. I certainly appreciate that, so thank you. So I also want to say one other piece, that I know that the staff of the engineering program is very proud of everything that you have accomplished. No matter what major you're choosing or what university you have chosen, the skills that you have learned in this program will serve you well. I have spoken to some of you. I know some of you are going on to engineering. You're going on to great places. Some of you are not. Some of you are majoring in business or what have you. But I know that the skills are going to help you. And I am confident that you all have very bright futures. And I'm glad to see that we were able to help you along that way. So it is my pleasure. I've been told by Mrs. Carroll that you guys have met the requirements and your other teachers for the PLTW engineering program, and it is my pleasure to say that you are going to graduate from the PLTW engineering program here at Seneca High School. As a memento of your hard work and dedication to finishing this program, and I know you're all aware of this because Melanie, for those of you who don't know, right, Melanie had to go to college early. Congratulations to her. But we went down to the class and we presented her, along with her mother could come and visit, presented one of these cords. So the students will be able to wear these cords. They're teal and white, and they are a memento from Seneca and show their pride in the engineering program here at Seneca, and we are happy to do that for them. So right now, what I would like to do is call them up individually and give them those cords. And Mrs. Carroll is going to help me.
Yes. So as you get called up, you're going to stay on stage. You're not going to leave. Okay? All right. So our first graduating student is Shannon Marie Briggs. Next we have Morgan Calabria. Samantha Durkis. Ryan Eno. Sebastian Friend. Madison Grudy. Austin Gupta. Grace Heineman. Anthony Johnson. Ryan Lawless. Kanan Ladawi. Christopher McCauley. Brady Moore. Sarah Moschini. Hannah Packard. Ethan Pfeiffer. William Schneider. Zachary Sinclair. Sheridan Smith. Olivia Spector. Carly Toole. And our two unfortunately absent students are Ryan Hartman and Melanie Weaver, and they are at college.